Good day, everyone. Today we will discuss the large scale assessment in science education. The major question to address in this session is what are the trends and prospects for the future of large scale assessment of science learning? The session focuses on changes in large scale assessment in science education at international, national, regional, and district levels. In the early years, one of the purposes of assessment is for international comparisons. A major reason for conducting international large-scale assessment is to shed light on the process and context of education by examining these processes and contexts comparatively. Secondly, another purpose of assessment is for accountability. Accountability systems can effectively communicate expectations and stimulate teachers and schools to modify their teaching and work to attain established performance goals. Assessment, especially summative, is used to determine students' learning and level of proficiency. In addition, assessment is used as a tool to evaluate the effectiveness of a certain program. Large-scale assessment encompasses various assessments that differ in their purposes, formats, and other features. The number of countries participating in regional, national, and international assessment has grown rapidly. Associated with this growth has been an increase in research into the impact of national and international assessment programs on educational policy, teaching, and learning practices. Wagner et al. Claim that the usefulness of an assessment is more rapidly expanding and where the empirical base is less developed. The usefulness of an assessment for a particular country depends on first, who get tested, second, what get tested, third, when this test occur, fourth, how a test take place, and fifth, why a test take place. Certain prevailing characteristics of large-scale assessment present significant benefits and risks to science education. This session, we will give an overview of four issues that will grow if the upcoming increased number of assessments continue mostly to have the same characteristic as ones currently in use. Increased large-scale assessment offers both great opportunity and substantial risk for science education. Requiring science assessment help ensure that science gets attention in school. This is particularly true for the elementary grades where teachers must balance and choose the amount of attention to all subjects, but it also has implications for secondary levels of schooling. Particular kind of assessment can help to promote more effective teaching and learning of science for all students. But there is also the danger of assessment pushing teaching and learning in undesirable directions that are counterproductive to the goals of scientific literacy. There is a danger, too, of missed opportunities to push the current state of the art to the new levels required to have an assessment systems that truly support accountability and classroom assessment purposes. Presented in your screen are some of the benefits and risks of more of the same assessment. One of the benefits of assessment is for accountability tests serve to focus instruction. Teachers and principals indeed pay attention to what is tested and adapt their curriculum and teaching accordingly. Second, teachers model what is assessed. They tend to model the pedagogical approach reflected on high visibility tests. When a state or district assessment is composed of multiple choice tests, teachers tend to rely heavily on multiple choice worksheets in their classroom instruction. However, when the assessment use open-ended items and or extended writing and rubrics to judge the quality of student work, teachers prepare students for the test by incorporating these same types of activities into their classroom practice. Third, test scores show initial increases. When a new assessments and accountability provisions are put into place, student scores show an increase at least for the first few years. Such sustained attention to test content and format tends to show up in test performance. Although these first points demonstrate some of the benefits of assessment, other research showed unintended consequences. School focus on the tests rather than the standards, with sanction and incentives riding on the test performance. Educators appear to give their primary attention to what is tested and how it is tested rather than to the standards underlying the test. Teachers shift how much classroom instruction time is accorded to core curriculum subjects, depending on whether or not a particular subject is tested at the grade levels. Second, what is not tested becomes invisible. As a corollary, focusing on the test rather than the standards also means that which is not tested tends to get less attention or maybe ignored altogether. Both the broader domain of the tested disciplines and important subjects that are not tested may get shrift. That a number of studies have found that the state tests tend to give relatively little attention to complex thinking and problem solving and instead tend to focus on lower levels of student performance, thus a strong implication for what is likely to be taught. Moreover, when tests and standards are not well aligned, it seems clear that the tests and not the standards will be the focus of attention. Test score increases appear to be inflated. If teachers teach only to the test and not to the larger domain that the test is intended to represent, the test score's results may represent just that the higher score on a specific test and not genuine learning that generalizes to another domains of science instruction. Research findings showing disparities between students' performance on the state accountability test and that on other achievement measures that are intended to measure similar areas of learning raise questions about the meaning of increasing test scores. Another issue in large-scale science assessment is the use of more varied types of assessment items. This barrier to congruence stems from emphasizing use of multiple choice and short open-ended items, or also referred to as constructed or free response items, because the former type of item cannot adequately interrogate the whole spectrum of science standards held by the science education community. Multiple choice and short answer type items tend to dominate in large scale accountability tests for several reasons. Many of them can be included within the testing time available, permitting assessment of as many domains of science content as possible. Furthermore, this type of item can be more expensively scored than open-ended items. However, large-scale assessments certainly have employed other type of items. For example, several international comparisons have included performance-based assessment as an option for participating countries. Some science assessment included practical tests for subsets of sample. Some countries or some regional examination boards have historically used laboratory practical as part of a large-scale high school exit examination. Multiple choice and short answer items can be different or more complex than the routine fare. Others assessment develop science assessment where the distractors in multiple choices items are based on research about students' misconceptions rather than mostly being based on the psychometric analysis of whether they adequately discriminate between high and low performing students. There are also some assessments, like for example, the Israeli matriculation examination, where they use short answer item in biology. It provides students with a multiple choice item and identifies the correct answers, but then asks students to explain why the response is the correct one. Other similar items require students to identify the correct answer first before asking them to explain their answers. However, the multiple choice and short answer items that most commonly are employed in large-scale assessment can go only so far in tapping the complex thinking, communication, and problem-solving skills that the students will need for further success. Rather, multiple measures are needed to address the full depth and breadth of our expectation for student learning. In addition to multiple choice and short open-ended items, large-scale assessments can include such items as more extended constructed response items, varying from responses involving sentences or paragraphs to full essays, concept maps, and performance based science tasks involving hands on problems with materials or computer based simulation of phenomena or data. Science performance assessment can address aspects of knowledge that multiple choice items cannot, but they bring their own challenges, such as not always tapping higher order thinking, and they are expensive to develop, administer, and score. Another prevailing issue that the large scale assessment must address is the assessment for all. Just as the science education community continues its quest to reach all students, large-scale assessment need to be designed in ways such that all kinds of students have equivalent opportunities to succeed at taking them. The science education community has for some time adopted the goal of reaching all students with science instruction. There are related issues in devising and administering large-scale assessment for which all kinds of students have equal opportunities to demonstrate their learning. Researchers have investigated gender differences in large-scale science assessment. Assessment historically have not accommodated well the needs of students with disabilities. In addition, there are researches that reveal more challenges than were recognized in the recent past years, no, for producing tests originally developed in English for use by students of other languages and from different cultures. This issue is for a critical importance in international assessment. Research has shown that the test translation for science and other subjects does not guarantee full test equivalence. International and some national assessment now employ a process of a back translation to reveal differences in meaning. Developers of large scale assessment have for some time been on the lookout for cultural bias during item development. However, studies of how cultural differences as well as language differences generate variation between translated and untranslated versions of science tests. Assumptions about the experiences and cultures of English learners combined with the test developers' limited experiential knowledge about students' home and community lives led to the greater than anticipated inadequacies in the test development. These emerging results suggest that different test development methods may need to be considered in the future if such sources of variation are to be fully addressed. Another issue of the large-scale assessment is the alignment of a large-scale assessment with standards. Using assessment that are not adequately aligned with the standards for science education cannot provide adequate guidance to teachers on what to do differently. Alignment is the keystone of standard reform. If assessment results are to be used to provide feedback that helps schools and the teachers and students within them attain understanding described in the state standards, then it is essential that the standards and assessments be aligned. Although the vagueness and the lack of specificity of standards in many states can make any determination difficult, available evidence suggests that the alignment of current tests is problematic. Studies have been conducted by several research teams on the alignment of state or local assessment, which corresponding curriculum frameworks for science and several other subjects. The result of the research claims that the existing state tests do not fully cover intended science standards. A common omission in state assessment is attention to scientific inquiry. Furthermore, the state assessment tend to emphasize levels of knowledge and skills that are lower than those exhorted by the state standards. What is tested instead seems to be at least as much a function of the items that particular item writers are most adept at producing and those that survive psychometric field testing, such as items that are at appropriate level of item difficulty and that relate in empirically coherent ways to other items, as it is a function of what the sets of items will provide the most comprehensive and balanced view of how students are achieving relative to standards. The next part of the session will be discussed by Ms. Edeline Thomas, will focus particularly on the more and different international science assessments.
Good afternoon, everyone. We have here the continuation of a report on the large-scale assessment in science education. We have here the next slide, which is on the more indifferent international science assessment. First, let's have the PISA, or the Program for International Student Assessment. It is a triennial survey of 15-year-old students around the world that assesses the extent to which they have acquired the key knowledge and skills essential for full participation in society. The assessment focuses on the core subjects of reading, mathematics, and science. Students' proficiency in an innovative domain is also assessed, and in 2018, this domain was global competence. The next one is the TIMSS, or the Trends in International Mathematics and on Science Study. So the teams conducted every 4 years at the fourth and eighth grades. So teams has a quasi longitudinal design with the fourth grade student cohort assessed for 4 years later at eighth grades. Assessing the fourth grade students can provide an early warning for necessary curricular reforms, and an effectiveness of this reform can be further monitored at the eighth grade of 4 years later. The next one, we have the PEARLS, or the Progress in International Reading Literacy Study. So the PEARL is an international comparative assessment that measures the student learning in reading. So the pearls document the worldwide trends in the reading knowledge of the fourth grades, as well as the school and teacher practices related to instruction. We have also the uh, Southeast Asian Primary Learning Metrics. So the SEA-PLM Learning Assessment program designed for the Southeast Asian context. So it is the result of the close collaborative work with the CIMEO member countries, and it includes background questionnaires for students, parents, teachers, and principals. The next one is the uh, Southern and Eastern Africa Consortium for Monitoring Educational Quality, or the SACMEQ, that consists of 16 ministries of education in the Southern and Eastern Africa. Among all those international assessments, we have here the two international or large-scale assessment or in terms of the science and mathematics. So first, we have the TIMSS, or the Trends in International Mathematics and Science Study, which is it is an initiative of the International Association for the Evaluation of Educational Achievement, which is the IEA. And we have also the PISA, or the Program for International uh, Student Assessment, which is an initiative of the Organization for Economic Cooperation and Development, or OECD. We have here the timeline of PISA and TIMSS. So every 12 years, PISA and TIMSS align in that the results are released more or less simultaneously. As in the case of this, uh, when only a week separates the results of the two studies in 2015. So PISA, in PISA, every 3 year, the students is tested in the program, which examines scientific reading and mathematical literacy levels. And on teams, every 4 years, samples of students undertake the teams, which examines the students' achievement in mathematics and in science. The PISA looks at 15-year-olds who is in most countries are approaching the end of compulsory schooling, and asks how they are able to apply understandings and skills in science, reading, and mathematics to everyday situations. While on teams, on the other hand, looks at how well the grade 4 and the grade 8 students have mastered the factual and the procedural knowledge taught in school, mathematics, and the science curricula. The PISA is the Program for International Student Assessment, organized by the OECD, or the Organization for Economic Cooperation and Development. It is a triennial international test first administered to 43 participating countries in the year 2000. So the PISA looks into the extent to which the 15-year-old students near the end of their compulsory education have acquired the knowledge and the skills that are essential for full participation in the modern societies, with emphasis on how well the students can extrapolate from what they have learned and can apply knowledge in unfamiliar settings, both in and outside of the schools. This approach differs from the other assessment that focuses on the student's mastery of knowledge and skills from a specific curriculum. The PISA assessment covers three foundation domains, namely the reading literacy, mathematics literacy, and scientific literacy. The focus shifts among these three domains for each assessment cycle, with the focus domain tested in greater detail than in two minor domains of the cycle. So, in 2019, the country's average score in reading was 340 score points, and in mathematics and science, the students in the Philippines scored 353 and 357 points. So, conducted, we have also here the TIMSS. Conducted every 4 years at the 4th and 8th grades, TIMSS has a quasi-longitudinal design with the 4th grade students cohort assessed for 4 years later at the 8th grade. Assessing the 4th grade students can provide early warning for necessary curricular reforms. So, in addition to mathematics and science assessment, the team's schools, teachers, students, and home questionnaires gather extensive information about the contextual factors at a school and home which are associated with learning and students' achievement. This includes details on how the education system is organized to facilitate learning, the students' home environment and support for learning, school climate and resources, and how instruction usually occurs in the classroom. In 2018, the Philippines scored 297 in math and 249 in science, according to TIMSS 2019 by the International Association for the Evaluation of Educational Achievement, or IEA. We have here the comparison table of PISA and TIMSS. We have here the three categories to be compared. We have the areas assessed, the target population, and the focus of assessment. Under the areas of assessed, we have here under the PISA, we have here the scientific literacy, reading literacy, and mathematics literacy. While on TIMSS, it we have only two fields, which is the mathematics and the science. And on the target population under PISA, all the 15-year-old students can participate the uh, assessment. And on TIMSS, only the grade 4 and the grade 8 students can participate the assessment. On the third one, we have the focus of assessment. It tests on the PISA, it tests on how well the students apply understanding skills in science, reading, and mathematics to everyday situation. While on the teams, it tests on how well the students have mastered the factual, procedural knowledge taught in school. So we have here the question, can the scores of the PISA and teams can be compared directly? So the answer is no. Although achievement in PISA in both teams year 4 and year 8 are described on a scale in which 500 represents the international average, each scale is based on a different group of participating countries. We have here the first reason. The international average for PISA is the average of the OECD member countries participating in PISA, which comprises around half of the total number of the participating countries. And the second one is the international average for teams is the average of all the participating countries, including developing countries. The scores for Year 4 and Year 8, or the Grade 4 and the Grade 8 in the Philippines, in TIMSS cannot be compared because not all countries test both year levels.
I will present the changes in national assessment of educational progress, and to close our discussion in large-scale assessment, I will present our criticisms on PISA as a result of the group's discussion and online research. NAEP, or the National Assessment of Education Progress, is a nationwide assessment in the US. This is equivalent to National Achievement Test in the Philippines. The National Center for Education Statistics creates, administers, scores, and reports the result of NAEP using a complex and sophisticated system to ensure highest form of reliability, validity, and accuracy. First, they develop the framework by identifying the focus of assessment. Second is the creation and reproduction of test items and materials. Note that they only select participants from NAEP schools. In the Philippines, every student takes the test. Students need about 2 hours to answer the test, and the result will be published in about 6 months after its administration. NAEP is administered annually, focusing only on specific disciplines each year. For example, in the first year of its implementation, science, citizenship, and writing were the focus of the test. The following year, in 1970, the focus was on literature and reading. In 1971, it was on music and social studies. Thus, science is assessed in a cycle of approximately 3 years. Each science assessment is also unique. For instance, in the first year of its administration, practical skills tests are included, while in the third, items were added to measure students' attitude towards science. In 1986, NAEP Science investigated students' home environments and the kinds of science instruction they received in school. An experimental assessment was also developed to test higher order thinking skills, and students interacted with a computer simulation for an item. In the 90s, NAEP conducted state-level assessments in reading, math, and science. In the Philippines, this is equivalent to School Achievement Test, Division Achievement Test, and Regional Achievement Test that were immediately abolished. Just imagine taking this test together with National Achievement Test and the final exam all in the same month. High school transcript study was also included during the recent assessment to survey the curricula being implemented in high schools and the course-taking patterns of students. The study provides information about the types of courses that graduates take, how many credits they earn, their grade point averages, and the relationship between course-taking patterns and graduates' achievement based on their performance on the National Assessment of Educational Progress in 12th grade. To summarize, these are the major changes in NAEP. First, it was launched in 1969. The test was expanded until it includes survey in 1976, students' home and school education, and higher order thinking skills in 1986. In 1993, three levels of achievement according to scores were specified as basic, proficient, or advanced. Then state level assessments in 1996. Test items measure students' knowledge and skills, a combination of cross-cutting concepts in either uses and transformation of energy and energy conservation or geochemical cycles, and either of the four practices: identifying science principles, using science principles, scientific inquiry, and technological design. Content of NAEP also varies across each grade being assessed. In grade 4, content is roughly equal across physical, life, earth, and space sciences. During grade 8, emphasis is more on earth and space sciences, while in grade 12, it is more on physical and life sciences. Maximum of 50% of test items have choices such as multiple choice, cluster, multiple choice, and predict, observe, explain, multiple choice. In the rest of the test, students are required to construct their own answers such as concept map, hands-on performance tasks, and interactive computer tasks. There must also be coherence among different level of assessments. Its coherence with instruction and curriculum is called horizontal coherence. Vertical coherence, on the other hand, requires that all education systems must have a shared vision for science education the purpose of assessment, and the definition of competence. While a system is developmentally coherent when it attends to how students' science understanding develop over time. Due to this, National Research Council developed a model for states to adhere to called Systems for State Science Assessment. One hugely satisfying advantages of these assessments is that we can see trends in education progress, such as in this figure, where, interestingly, science continuously progressed from its downfall in the 80s. While we acknowledge the immense benefits of joining a large-scale assessment, we noted, based from research, some criticisms on ILSAS. We will focus here on PISA. First, let us give you an idea why PISA is so popular that it even surpassed the older TIMSS. It started marketing itself on three founding questions. As it turned out, the stunt was effective despite numerous criticisms it receives. Perhaps the most controversial is their claim that if a country's OECD increases, its economy improves as well. This claim was heavily challenged by a number of scholars. First, the test score is from TIMSS, not from PISA, because they did not have exams until the year 2000. Second is the invalid analysis. Test scores taken in a year is correlated to economic growth of the same year to which test takers are not yet in the workforce. They should have waited for them to enter workforce in the next 2 to 4 years. But even so, studies that carried out these suggestions found no relationship between test scores and economic growth. Next, PISA claims that it measures knowledge and skills necessary for one to live and succeed in life. Upon close analysis by researchers, they found out that questions in PISA, just like TIMSS, also measure general cognitive ability. It is not different. Further, PISA showed no research on current or future trends to which they based their questions upon. PISA's view of education is monolithic. It states that there is a set of skills and knowledge that are universally valuable in all societies, regardless of their history and future. Well, every country is unique and meet different challenges which require different sets of knowledge and skills. PISA's view of education is very narrow that it only focuses on economic growth and competitiveness, thus caring less on fields such as art, humanities, and the social sciences. As a result, high-scoring countries have students with low science interests and attitudes. PISA science scores tend to be negatively correlated with future science orientation, job, entrepreneurship, confidence, and well-being. Moreover, high PISA scoring education systems tend to have an authoritarian orientation, thus explaining PISA's claim that students from high-scoring countries blame themselves for their failure, while students in low-scoring countries blame their teachers and the school. It is not because of learning responsibility, but because of the freedom to speak. Sampling method is also scrutinized as it bases on age rather than on curriculum level. There are also reports that some school systems, such as in Beijing, excludes immigrants in taking the test. Critics also noted that test instruments are biased in format, language, culture, and text types. For example, in Nordic countries, PISA reading assessment tend to be biased against boys. PISA instruments are also of more Western inclination and are biased against Middle East and Asian countries. Discrepancy between PISA items and Greek textbooks were also noted. In terms of language, German versions are 18% longer but requires the same amount of time to take. We can also assess these components to determine if they in the Philippines are biased by PISA tests. Craner and Christensen also found that PISA uses a Rush model inappropriately in its literacy data. Thus, the resulting country rankings are not robust. Another disturbing effect of PISA is how it hinders innovation in education. China was about to reform its rigid exam to give way for creativity and diverse talents. But PISA results imply you have the best education in the world, so they stopped the reform. Japan had relaxed its education system for the same reason. However, upon implementation, they ranked low in math. This made them go back to their old systems. Finally, we present here the findings of the critical analysis of 20 scholars from European countries. Their major concerns were: PISA is by design culturally biased and methodologically constrained to a degree which prohibits accurate representations of what actually is achieved in and by schools, nor is there any proof that what it covers is a valid conceptualization of what every student should know. The product of most public value, the national league tables, are based on so many weak links that they should be abandoned right away. If only a few of the methodological issues raised in this volume are on target, the league tables depend on assumptions about the validity and reliability which are unattainable. Lastly, the widely discussed byproducts of PISA, such as the analysis of good schools, good instruction, or differences between school systems, go far beyond what a cautious approach to this data allows for. They are, more often than not, speculative. If PISA, as well as TIMSS, do not change based from these criticisms, or if they continue to interpret their results beyond what the data is capable of, then education systems should either use PISA results with extreme caution or simply stop participating from it. That would be all. Thank you.